Hello everyone, my name is Laila Linke and I'm very pleased to present today Euclid, ESA's dark universe detective whose goal it is to shed light on the dark components of the universe. So I think we have a pretty good picture of what the universe looks like and how it evolved. About 14 billion years ago, the universe was started with the Big Bang. After that, we had a period in which the universe expanded almost linearly until the emission of the cosmic microwave background. Afterwards, the universe continued expanding, but with a slowing phase. And only in recent times has the universe begun to expand, actually accelerated. And with this picture of the universe, we also have an idea of what the universe is actually made of. And the interesting and mysterious part of that is that ordinary matter, so the things that all of physics is concerned with, only makes up about 5% of the total energy matter budget. 25% of the energy matter budget in the universe is made up of dark matter, which is a form of matter that does not interact with light, but needs to be there because it is required to form all the structures we see today. And 70% of the energy matter budget is composed of the mysterious dark energy, which is the force driving apart the universe and causing the accelerated expansion. The question there, though, is what is this dark matter? What is this dark energy? Both of those components are completely unknown to us and cannot be found in a laboratory, at least until now. And do these two components mean that maybe our understanding of gravity is actually not the correct one? Do we need a new physics, new model of gravity on cosmological scales? To study this, we can actually look at the structures of dark matter. So dark matter in the universe forms a sort of web-like structure as shown here in this picture. This picture is from a cosmological simulation. Everything that is bright is a high-density region. Everything that is darker are so-called voids. So you see this net-like, this web-like structure. And if you're looking at these dense regions, the size and the number of those dense and underdense regions depends a lot on what properties dark matter actually has. So if we study these, we can find out how dark matter clusters, if it interacts with itself, and so on. Now, we can also look into the past of the structure. Every time we look in the universe, we look in the sky, we essentially look in the past anyway. So we can look at this structure throughout the expansion of the universe. And with that, we can actually find out how this structure evolved, which depends on how the universe expanded, and in turn depends on what dark energy actually does. And then finally, we can also compare these dark matter structures to theoretical model to see if the standard theory of gravity actually still holds up, or if we need to adapt it. Now, the problem with this picture is we cannot actually see dark matter. So what do you do to actually make the invisible visible? And this is where galaxies actually come in. You can think of it as in a similar way as a dancing couple where the guy has a really dark suit and it's nighttime, so you can't really see him. But the woman has a really bright dress, so you can actually see her. And in this case, the guy in the dark suit is the dark matter, and the woman in the bright dress are actually the galaxies. And we can infer where there are a lot of galaxies, there's also a lot of dark matter. So just to show it a little bit more visually, so what you see here is an image of different galaxies on the sky, and overlaid here is the dark matter distribution. So we see again this web-like structure, and as you might have seen at the beginning of this video, where there's a lot of dark matter, there's also a lot of galaxies. So what we need here are the 3D positions of many, many galaxies, and from that we can essentially map where the dark matter is. Another way to make the invisible visible is by the gravitational lensing effect. So the idea behind gravitational lensing goes back to general relativity. So if we have a large mass, as for example this galaxy cluster that you see here, this large mass will bend space-time, which is illustrated here by this rubber sheet-like lines on here. And because space-time is curved now, the light from this distant galaxy on its way to us here on Earth is no longer traveling along a straight line, but actually along these curved lines. And this means that the image that we see of the galaxy is actually distorted and no longer the same shape as you would have observed if there was no galaxy cluster between us and the galaxy. And that means that when we're looking at the night sky, essentially we're observing something similar than when we are looking at a swimming pool in summertime and the water is moving around. So we know that the actual tiles of the swimming pool are actually, rectangular lines, squares, whatever. But what we see is actually a distorted image. And this distorted image is, in this case, due to the water. But in reality, the distorted images that we will see are due to dark matter, which are distorting the images we see of background sources. So in analogy, essentially what is happening, usually in a swimming pool, we have tiles and they are distorted to form these irregular shapes. And in the universe, we have galaxies. Those galaxies are on average round. And due to the distortion by, for example, a large galaxy cluster or other dark matter distributions, we will see distorted shapes. In here, this effect is very, very exaggerated. In reality, it's only about 1% of the shape of a galaxy that is due to the distortion by gravitational lensing. And that means we need many, many, many of those shapes to actually detect the signal at all. And the more galaxies you observe, the better you can detect the signal. And this is exactly where Euclid is coming in, our dark matter detective. So this is what Euclid looks like. It's a space telescope with a 1.2 meter mirror inside of it. It has been launched in 2023 and is currently orbiting the Lagrange point L2 and trying to observe the universe. So it has two instruments on board. It has an optical imager that takes essentially pictures in a similar way as your camera might do. And it also has a near-infrared instrument on it, which takes images in a slightly longer wavelength, which is very, very helpful to detect galaxies that are very far away because their light is redder than the light of the galaxies that are nearby. And it also takes spectra, which are helpful to actually get the distances, so the full 3D positions of galaxies. And with these two objects, with these two instruments, what Euclid is doing is it is observing basically all of the night sky where we can find galaxies. So this is the night sky shown here, and everything that is blue is going to be observed by Euclid. And you see that this is basically all of the sky that is not covered up by the Milky Way in front. So everywhere we can observe galaxies, we will observe galaxies using Euclid. And the way it does that is illustrated here on the other side. So it's just staring at the sky, moving up and down, and observing every part of the sky exactly once, and then trying to find as many galaxies as possible inside of this tile that it has observed. So when I say Euclid, I do not mean only this instrument, but actually a large consortium of people who are working with this data, who have made it possible for this telescope to be launched, and who are now eagerly awaiting the data and already trying to deal with the data for the scientific exploitation. The whole consortium includes more than 2,600 scientists all over Europe, Canada, Japan, and a couple of people in the US as well. And we are responsible for the instruments, for collecting the data, and also for the scientific exploitation. And this is a huge effort, which is why I wanted to show this picture showing at least some of my colleagues inside the Euclid consortium. So, as I said before, Euclid was launched on the 1st July of 2023, but it was a long road to this space mission. So the proposal of the Dune and Space, which are the precursors for Euclid, was already in 2007, and only in 2011 Euclid was actually selected as a merger of those two proposals. But you can see from 2011 to 2023, it's a long while. The project formally started in 2012, and since then the instrument had to be developed. There were some setbacks. Originally, Euclid was meant to be started on a Russian Soyuz rocket, which was no longer possible after the Ukraine war. So finally, it had to be moved to a SpaceX rocket to be launched on time in 2023. So just a couple of images of the actual launch. So this is the last image that an actual human could take of Euclid before it was put into its fairing to be sent into space. Here it is transported out of the hall at Cape Canaveral to be put onto the rocket. Here it is on top of the rocket. And then finally, there was the very exciting day when Euclid was finally launched Here she goes, up into the sky. And you might wonder, where is it actually going? Well, Euclid is currently at the so-called L2 point, Lagrangian L.2, which is about 1.5 million kilometers from Earth, as you can see here. So it's far out. There's no possibility to send an astronaut there to repair the mission if something has gone wrong. So we had to really make sure that everything is okay, so that this telescope could actually work on its own completely. But it is in good company. The Gaia satellite was there as well, and JWST, the James Webb Space Telescope, is also at L2. Here you can see how Euclid is actually moving up to L2, captured by a ground-based telescope, and you see it here traveling in front of the stars. So what are the actual images looking like from Euclid? So this is one of the first images that was taken, and it's already breathtaking. This is the Perseus cluster, a large galaxy cluster, and these two galaxies here, these are the brightest galaxies of this Perseus cluster. And basically every point you see on here, with just very few exceptions, are all galaxies. So you see that Euclid really is able to capture thousands of galaxies in a single image here. And what I always find even more interesting is that you can zoom into this image. And let's zoom into this part over here, and you still get a crystal clear, sharp, fully resolved image, and you see a lot of distant galaxies over here. So in general, if a galaxy is redder, it's usually further away. And you see that these galaxies are really, really red compared to the cluster galaxies over here, so they are far behind the cluster. And with those galaxies, you can actually try to measure the mass of this galaxy cluster, and you get masses in the range of 10 to the 14, 10 to the 15 solar masses for those really massive galaxy clusters. So what makes Euclid really, really special is its large field of view. So you probably know the Hubble Space Telescope, which has a resolution that is quite similar to Euclid. You probably also know the James Webb Space Telescope, the JWST, which has an even higher resolution than Euclid. But Euclid has the unique feature that it can capture a large field of view at the same time. And this you can see illustrated here on these slides. So this is the famous Horsehead Nebula. You might know of it. It's in the constellation of Orion. And with a single Euclid image, you can take both the Horsehead and a large part of the rest of the nebula as well, and a lot of sky as well above that. So it's a huge image. And if you just take an image with Hubble, you see you only get a much smaller area in one pointing, and with Webb, an even smaller pointing. So if you were to use Webb to actually capture all of the 15,000 square degrees that Euclid wants to capture, it would take decades, maybe even hundreds of years. So this is why we really, really need Euclid, which has both a sharp resolution and the large field of view. So there were a couple of really, really interesting things that were found with Euclid already in the first data releases that have come up. One of them is the perfect Einstein ring that was found by Euclid. So Einstein rings happen also due to gravitational lensing. If you have a mass in the foreground and, for example, a galaxy directly behind this mass, the image of the background galaxy will be distorted in a basically ring-like shape. And this was found completely by chance in one of the galaxies. So this is the full Euclid image. You can already see the ring, but when you zoom in, you see the actual ring over here. So these four bright spots that form one ring together, these are one galaxy that has just been completely distorted. And you have a foreground galaxy. Here, this is the big point in the middle. And the interesting thing about this is that this foreground galaxy, this whole blob over here, was known since the 1800s. So even with really basic telescopes, it was already possible to see this galaxy, granted with probably better skies than we have today. But this Einstein ring was never found, not by any of the previous telescopes at all. And you really needed the sharp resolution that Euclid provides, together with the fact that it's just surveying so much data, to actually find this brilliant Einstein ring. Another really great finding of Euclid so far are thousands of new dwarf galaxies. So dwarf galaxies are galaxies that, in contrast to our Milky Way, have much less mass, much less stars, and not only are they comparatively smaller, but they're also usually less bright, more dilute across the sky. So it's much more difficult to actually see them, to actually find them. You need to be essentially sure that you're not just detecting the background or some remnant of the Milky Way. And with Euclid, it was possible to find thousands of new dwarf galaxies. So in an area that was about 8 times the full moon, almost 3,000 new dwarf galaxies were found. You can see some of them here on this image, and you already see that they are quite dilute. So they don't differ too much from the background. So you need an instrument with really high fidelity, with really high sensitivity to these low surface brightness objects. And this was basically only now possible. And now that we have all these many dwarf galaxies, we can actually do some science with them. The interesting thing about dwarf galaxies is not only are they not as bright as the giant galaxies like the Milky Way, but they also have much more dark matter compared to their mass. And that means that they are ideal laboratories to find out about the properties of dark matter. So if you see all those dwarf galaxies, you can look at those properties of those galaxies, you can see how the stars behave in there, and from that you can try to compare that to different models of dark matter, different particles that might make up dark matter, and these dwarf galaxies help you in determining which of those models is actually possible and which of those can be excluded. And this is why those dwarf galaxies really are important. So going further, where are we going with Euclid now? So the launch was in 2023 in July, and the first images were already released in November. In February of 2024, the full sky survey, so these 14,000 square degrees across the full sky, were started. And in March of 2025, we had our first small data release, which is where the results come from that I've already shown you before. But right now, we are all working towards our first big data release, and that is expected to come in fall of 2026. And there we will actually give the first cosmological results, meaning the first results on how dark energy behaves, the first results on how much dark matter there is in the universe, coming from Euclid. And well, then the mission will continue. The nominal end is 2029. There are some talks of maybe a possible extension, but this is not fixed at all. But yeah, basically, we expect to have the final word from Euclid on cosmology about 2030, when we are finished with analyzing all of the data that we are getting from Euclid. So, just in a nutshell, what I wanted to talk about, the dark universe is still a puzzle. What is dark matter? What is dark energy? What do they make up? And Euclid is really trying to help us provide answers by mapping out the dark matter structures using both the positions of galaxies and the weak gravitational lensing effect, both of which help us to make the invisible actually visible. And yeah, the mission has successfully started, and I just want to highlight that the first 53 square degrees, so the small data release we made, already led to more than 50 science papers. And we really hope that the full 14,000 square degrees will not lead to 14,000 papers, because we cannot write all of them and probably cannot read them as well. But it is clear, I think, that there will be very, very many interesting science results coming out of Euclid, in particular on the dark universe. So if you're interested in learning more, there are some web pages from both the Euclid Consortium and also from ESA on Euclid. Both of them have sections which are also written for non-scientists, and of course press releases and interesting results will also be published there. So I encourage you to keep an eye on these if you're interested in the topic. And with that, thank you very much for your attention. I'm looking forward to your questions in the live session, and I hope you enjoyed my talk.